Good morning everyone. I welcome you all in this video, that is interference in thin films of non-uniform thickness, which we call it as wedge shaped thin film. This topic or this video is in continuation with our previous videos on interference in thin films of uniform thickness. So here we have a film of non-uniform thickness. Non-uniform means that if we consider two planes over here, plane OX dash and OX, if these two parallel planes are inclined at an angle theta, then this plane forms a wedge shaped structure where the two ends of the surface meet at a point O, and at that point the thickness is 0, and as we move away from this point of contact of these two plane surfaces, the thickness of the film gradually goes on increasing. So two planes OX dash and OX are inclined and meet at a point O, and wherever it meets at a point O, it makes an angle theta. Such type of film we call it as a film of non-uniform thickness, because the thickness in the whole region of this film is not uniform. It is going on varying from the point of contact towards the outer side. So this we call it as a wedge shaped film. Now in case of wedge shaped film, we will study the interference in wedge shaped film and interference due to reflected light. So in this case, first of all, I will explain the diagram completely, then we will evaluate the path difference in this wedge shaped film. If we see the diagram over here, OX dash is one plane surface, OX is another plane surface, and light from a monochromatic source falls on the upper surface of this wedge shaped thin film. The ray AB falls on the upper surface of wedge shaped film. From point B, the ray is partially reflected along BR1 and partially it is refracted along BC. From point C, the ray is again reflected along CD, and from point D, it emerges out as DR2. So the ray BR1 and DR2 are derived from the same monochromatic source. So both the rays are coherent and they will superimpose to give rise to an interference pattern. Now if we see the distance, then the ray BR1 has travelled a longer distance in comparison to ray DR2. So from point D, we drop two perpendiculars. One perpendicular we are drawing on the ray BR1, that is DF, and another perpendicular from point D, we drop this dotted line on the ray BC. Now here we see that from point B, if we see, that is from the plane surface OX dash, we draw a normal. This dotted line is the normal on the surface OX dash which is extended towards the downward side, and we have another normal, that is NM. This normal is plotted on the surface OX. Both the normals, if we see, then the normal NM is looking like a straight normal, whereas the normal, this normal, that is from BM, if we see this normal, then this normal is slightly inclined, because my surface OX dash is inclined, so the normal drawn on that surface is slightly inclined, and both the normals meet at some point M. So the angle between two plane surfaces is theta. So the angle between these two normals drawn on the plane surfaces OX dash and OX will also be theta. Second term. Now if I see the triangle BMN, this is my angle incidence and this is my angle of refraction R. So we know that the sum of interior angles is equal to exterior angles, that is this angle R and this angle theta of the triangle BMN, that is R plus theta, will be equal to this angle, that is R plus theta. So this angle, which is not shown in the diagram, this angle will be R plus theta. If this incident angle is R plus theta, then this side of angle will also be your R plus theta. Now second point, this angle is clear. Now if we see this part, if this angle is I, then from this dotted line, this complete angle will be 90 degree. So this angle will be 90 minus I. So point F will be 90 degree and this is my angle I. Same way, if I see over here, this angle is R. So from this normal complete, if I see this part, that is this whole part, this will be 90 degree. So this one will be 90 minus I, so 90 minus R, so this is my angle R. Now from point D, what we have done, we have extended, from point D we have extended the line and that line is further extended downward. Then if I see this part D to P, this line and NM, these two lines are completely parallel. DP and NM are completely parallel, and the line BCP, this line BCP, this line cuts these two parallel lines. BC is the ray and from point C we have extended the line, so it joins at point P. So BP, this line cuts these two parallel lines NM and DP. So we know that alternate angles are same. That means if this angle is R plus theta, then this angle will also be my R plus theta, and alternate angles and corresponding angles are also same. So if this is R plus theta, then point D, this angle will also be my R plus theta. So in this diagram, one more point we see over here is that if I see the point C, right angle triangle CLP and CLD. If I see the right angle triangle CLP and CLD, these both right angle triangles are congruent triangles. And for congruent triangles, we have the conditions that all the three sides should be same, or two sides or one angle should be same, or two angles and one side should be same. So, these two congruent triangles have this condition that both the angles are same and sides, this CL is same, which from this we can clearly say that my CD will be equal to CP and DL will be equal to LP. So this is my diagrammatically description of an wedge shaped film, and the thickness from D to L is T. So that's why from L to P the thickness of the film will be again T. So in this case, to evaluate the path difference between BR1 and DR2, as already I have mentioned, two perpendiculars were drawn, that is DF on BR1 and DE on BC from point D. So my path difference is equal to BC plus CD, this much distance travelled by the ray in the medium, minus this distance, that is BF in the air. And we know that a distance in air is numerically equal to mu times the distance in the medium. And in the air, the refractive index mu is equal to 1. Therefore, the path difference is equal to mu BC plus CD minus BF. Now, this is my equation 1. Now, here I have made some changes over here, that is path difference is equal to mu. Now, BC, I can write BC as BE plus EC, that is BE plus EC plus CD minus BF. So, what I will do it over here, I will use the Snell's law of reflection. Mu is equal to sin I upon sin R. So, in order to calculate sin I will consider the right angle triangle BFD. Right angle triangle BFD. So, in this right angle triangle, sine angle, we know that it is perpendicular upon hypotenuse. So, F is 90 degree. So, perpendicular is BF and hypotenuse part is BD. That is BF upon BD divided by sine R. So, in order to calculate sine R, we will consider the right angle triangle BED. That is right angle triangle BED, where point angle E is 90 degree. So, again angle sine is perpendicular upon hypotenuse. So, in right angle triangle BED, perpendicular component is BE and hypotenuse component is BD. That is BE upon BD. So, in this term BD and BD gets cancelled out. So, leftover term is BF upon BE, or I can write it as BF is equal to mu into BE. That is my equation number 3. So, now what I will do? I will substitute the value of equation 3, that is BF, in my generalized equation 2. So, my path difference is mu bracket BE plus EC plus CD minus, instead of BF, I will substitute mu into BE. So, if I open this bracket, so minus mu BE and plus mu BE gets cancelled out. So, my path difference is equal to mu EC plus CD. That is my equation number 4. Now what I will do, as we know that this NM and DP are parallel and BCP cuts these parallel lines. So the triangles CLP and CLD are congruent, and since angle CDL is equal to angle CPL, this angle and this angle is r plus theta, and angle DLC and PLC is 90 degree. So CL is the common axis. Therefore, DL is equal to LP, that is equal to T, which is the thickness of the film. So as these two triangles are congruent, so their sides, that is CD, will be equal to CP. So in the previous slide, my path difference was mu EC plus CD, which is equal to EC plus CD. But CD is equal to CP according to the condition of congruent triangles. So instead of CD, I will substitute CP. And EC plus CP is equal to EP. That is my equation number 5. So now I have to calculate the value of EP. So in order to calculate this side, that is EP, what I will consider? Again, I will consider right angle triangle EDP. So that is EDP. So in this right angle triangle, I need to get the value of EP. So I will consider the angle, that is r plus theta, which is cos r plus theta. And cos r plus theta is base upon hypotenuse. So this is my base, that is EP, and hypotenuse term is DP. So this is EP upon DP. So from here, EP is equal to DP cos r plus theta, and DP is nothing but DL plus LP, that is T plus T, that is twice T cos r plus theta. So my path difference is 2 mu T cos r plus theta, which is my equation number 6. Since the ray BR1 suffers the reflection at B on the surface of denser medium, it undergoes a path difference of lambda by 2 on reflection due to Stokes' law. So the effective path difference between two rays BR1 and DR2 will be 2 mu T cos r plus theta plus minus lambda by 2, which is my equation number 7. So now at the last, we will write the conditions for constructive and destructive interference pattern. So in order to have constructive interference pattern, the path difference should be an even multiple of lambda by 2. And our path difference is 2 mu T cos r plus theta. I consider the minus sign over here, that is minus lambda by 2. This is equal to 2n lambda by 2. That is 2 mu T cos r plus theta is equal to 2n plus 1 lambda by 2, where n starts from 0, 1, 2, 3 and it goes on. So when condition of equation 8 is satisfied at a particular point, the film will appear bright in wedge shaped film. Similarly, for destructive interference pattern, the path difference should be an odd multiple of lambda by 2, that is 2 mu T cos r plus theta minus lambda by 2 is equal to 2n minus 1 lambda by 2. So here the n will start from 1, 2 and 3. So this is equal to 2 mu T cos r plus theta. This is 2n lambda upon 2. So 2 and 2 gets cancelled out. So this is equal to n lambda, where n starts from 0, 1, 2 and 3. So when condition 9 is satisfied, the film will appear dark in wedge shaped film. Now in continuation with this topic, we will calculate the fringe width of wedge shaped thin film. Now we know that fringe width is nothing but it is denoted by omega, and it is the separation between any two successive bright fringes or between two dark fringes. So in order to obtain fringe width, in this diagram we will see, that is, we have the surface, two surfaces which are inclined at an angle theta, and from point A, that is from point of contact to this one T1, the distance is xn, and from point of contact to T2, that is at this point the thickness I have written as T2, and at this point the thickness I have mentioned as T1. So from point of contact to this point, the distance is x of n plus 1. So let xn be the distance of nth bright fringe from the edge A of the film as shown in the diagram. So we know that what is tan theta? Tan theta is perpendicular upon base. So here the perpendicular component is T1 and base is xn. So from here my T1 is xn tan theta, that is my equation number 1. And just now we have seen that the condition for bright fringe, we normally denote it as 2 mu t cos r plus theta is equal to 2n plus 1 lambda by 2. So if I substitute equation 1 in equation 2nd, I will get the equation 2 mu. Instead of t, I will write xn tan theta cos r plus theta. This is equal to 2n plus 1 lambda by 2. That is my equation number 3rd. Similarly, for another bright fringe, that is xn plus 1 is the distance of n plus 1 bright fringe from the edge A. So in the same way, I will write tan theta, that is perpendicular upon base. Perpendicular is T2 and base from the edge is x of n plus 1. So my T2 is equal to xn plus 1 tan theta. Equation number 4. So in the same way, I will substitute my equation 4 in my equation number 2nd. So I will get the value 2 mu xn plus 1 tan theta cos r plus theta. This is equal to, instead of n, I will write n plus 1. So my equation will be 2n plus 3 bracket close lambda by 2. That is my equation number 5. Now I will subtract equation 3 from 5. That is 2 mu xn plus 1 tan theta cos r plus theta minus 2 mu xn tan theta cos r plus theta. This is equal to 2n plus 3 lambda by 2 minus 2n plus 1 lambda by 2. So I see this side, I can take some parameter common over here. So common parameter is 2 mu tan theta cos r plus theta bracket xn plus 1 minus xn. This is equal to lambda. If I open the bracket, some terms gets cancelled out, so it comes out to be equal to lambda, where xn plus 1 minus xn is the fringe width, which I denote it by omega. So my omega is equal to lambda upon 2 mu tan theta cos r plus theta. If we have a normal incidence, say angle I equal to r equal to 0. So my cos of r plus theta will reduce to cos theta. So omega is lambda upon 2 mu tan theta into cos theta. And tan theta can be written as sin theta upon cos theta. So cos theta and cos theta gets cancelled out. So omega is lambda upon 2 mu sin theta, and for very small value of theta we can write sin theta as theta. So omega is equal to lambda upon 2 mu theta. That is my equation 7, and this is known as fringe width, and it depends upon the wavelength lambda and the refractive index of the film and angle between two plane surfaces. Thank you.